In this example, we're given a function xy squared and a rectangle e. We want to estimate the double integral of that function over the rectangle using a Riemann sum. Now, before we actually get to the example, I just want to talk a little bit about the idea of what we're doing here. The first thing to remember is that the way that we define any kind of integral, for example, the regular single variable calculus integral that we're familiar with, is as a limit of Riemann sums. Now, one issue with all this Riemann sum stuff is the notation. It can be a little intimidating and overbearing, but the general idea is that we start with a function. We want to compute the area under the curve. That's the motivation for defining an integral. How do we do that? Well, we can chop up our domain into sub-intervals, however many we like. In this case, I'm chopping it up into 4. And they don't even have to be the same length. And then over each of those intervals, I draw a rectangle. The height of that rectangle is determined by the value of the function at some point in that subinterval. A Riemann sum is just the area of these 4 rectangles. And then the integral, the true area, is defined as the limit as we send the number of rectangles to infinity. It's exactly the same in higher dimensions. The only difference is now instead of trying to compute an area under the curve, we're computing a volume under a surface. So given a function of 2 variables, the graph of that function is a little blue surface. And what we might want to compute is the volume underneath that surface sitting above this rectangle in the domain. Again, you may have seen some definition like this, where the double integral is defined as a limit of Riemann sums. The notation is horrifying. There's a lot of letters, there's a lot of indices flying around, and it's very unclear what we're doing when you just read something like this. But the general idea is that we approximate the volume using, instead of rectangles, using 3-dimensional boxes. So in the domain, we divide it into sub-rectangles, in analogy to what we did in the 1-dimensional case. And over each of those sub-rectangles, we draw a box. And I won't try to draw this because it'll only make the picture more confusing, so you'll have to just visualize boxes sitting above the little green squares. But the z height of each of those boxes is determined by the value of the function at some sample point in that rectangle. And it doesn't actually matter what point we pick. So this mess of sigmas and xij's and stuff like that, you can try to parse the notation if you want, but when you look at a Riemann sum like this, all you need to think about is add up volumes of boxes. That's it. Now, to get started, all we need to do is take our domain E, which is a rectangle, chop it up into 4 rectangles, however we want, and then use any sample point we want inside each of those rectangles to get the height of our boxes. So since I scrolled down, let me remind you what the function f was and what the rectangle e was, so that we don't forget. F of x was xy squared, and e was the rectangle 1 to 2 cross 2 to 4. Okay, so if I draw a picture of our domain, this will be a rectangle in the xy plane. The x range is from 1 to 2, and the y range is from 2 to 4. So probably not to scale, but it doesn't really matter. Just a rough picture. Here's our domain E. We need to compute a Riemann sum with 4 rectangles, so we just need to chop this up however we want. For example, this is just a matter of chopping the x direction in some way and chopping the y direction in some way. And again, these don't have to be equally spaced or anything like that. We have a lot of freedom based on the statement of the problem. So in particular, I could decide that I want this division in the x direction to be at, say, 1.5. And likewise, I could decide that I want the division in the y direction to happen at, I don't know, 3.5. Again, if you wanted to, you could make these equally spaced out and make it at 3, but you don't have to. So I can make it at 3.5 just because I want to. Now, having done that, we need to pick a point in each of these four rectangles to use as our sample point to get the height of the box. And again, we can pick any point that we want in each rectangle. The statement of the problem did not restrict us in any way. So for this bottom left rectangle, maybe I'll pick the point 1, 2. For this top left rectangle, I don't necessarily have to pick the lower left corner. I could pick, say, the top left corner, the point 1, 4. For the lower right hand rectangle, I could pick, I don't know, let's call this the point 2, 3. That does lie in this subrectangle. And then for the point up here, I could pick this top right corner. I could pick some point in the middle. Again, it really doesn't matter. So I can pick the point 2, 4. Now that we've decided our sample points, it's just a matter of computing the volume of each box sitting atop these four rectangles. So we could say, this double integral that we're trying to estimate is approximately the sum of the volumes of these four boxes. Now, let's look at the volume of the lower left box first. The width of that lower left box is 1.5 minus 1. The height of that lower left box is 3.5 minus 2. The height of the box is the value of the function at our sample point. So in this case, this would be f of 1, 2. And this expression here is exactly one of the summands right here. I have f of a sample point times the width of the box times the height of the box. So one rectangle down, and now we just need to compute all the rest of these. So this will be plus the lower right rectangle. The sample point is 2, 3. So that would generate the height of the box. The width, in this case, the delta xij would be 2 minus 1.5 times the height would again be 3.5 minus 2. That term right there is the volume of this box, and then we can move on. This top left box, the sample point we picked was 1, 4. The width is 1.5 minus 1 again. And the height this time is 4 minus 3.5. Then we have one more rectangle to compute. The top right box, the sample point we picked is 2, 4. The width is 2 minus 1.5, and the height is 4 minus 3.5. There you go. That, unsimplified expression is the Riemann sum. All we have to do is simplify this. That will be our estimation. So when I simplify the widths and the heights and then plug in the points to f, we get this expression. And then I'm far too lazy to compute all this by hand, so I'll plug this into Wolfram Alpha and see what numerical answer we get. Let E be any region in the xy plane, and we want to interpret the meaning of the double integral over E of 1 dA. Now, we just talked about how double integrals are defined for the purpose of computing volumes under surfaces, so you could say, Joe, this is just the volume under the surface given by the function 1. And you're correct. But the idea here is that we can interpret this a little differently. I'm going to give you the punchline initially, and then I'll give two different explanations to think about why this is the case. So it turns out that this double integral that we care about, this is exactly the area of the region E. Now again, you might object to this, saying, wait a second, double integrals compute volumes, but one really important thing to keep in mind is that integrals have no intrinsic meaning. An integral is a mathematical abstraction, and it can be interpreted in any number of ways, and this will come up a lot throughout the quarter. Now we can think about one explanation by starting with the volume interpretation. Let me draw a picture really quick. Here's our region E in the xy plane, and here's the graph of the function 1 sitting above it. The volume that we're computing is the volume of this coin. It's a region with uniform thickness 1. So we already know that the double integral over E of this region is the volume of this coin. But how do I take the volume of a coin shape like this, or rather, how do I compute the volume of a shape with uniform height? I just take the area of the base times the height. Well, this height here is the height of the function, which is always 1. So therefore, we're just left with the area of the base, which is the area of E. We can also think about this a little more directly using the definition of a double integral as a Riemann sum. To do this, let's pretend that our region is a rectangle. The Riemann sum definition of this integral would say what? It would say, well, chop up this rectangle into smaller subrectangles, however you want to do that. For example, we could chop it up into 6 different rectangles like this, and take the sum over those 6 rectangles of the horizontal thickness times the vertical thickness times the value of the function at any sample point. Well, the function is always 1, so the f of xij, yij thing right here, this is always going to be 1. So the only thing that we get in the summand is a horizontal thickness and a vertical thickness. Then we add them up, and we take a limit as the number of rectangles goes to infinity. Now let's just think about what we're doing right here. The summand is the area of one of these rectangles. So when I add up the area of all of those rectangles, I just get the area of the entire red rectangle. So this expression is just the area of the red rectangle, which is just the area of E. Now this was specifically for a rectangle, but you can imagine that this works for any region. If you set up a double integral of 1 and you think about what the Riemann sum is telling you, you're just decomposing any region into smaller and smaller subregions, computing the areas and adding them all back together. And in the limit, you recover the area of your original region. So anyway, the takeaway here is that even though a double integral computes volume, there's no intrinsic meaning to any kind of integral, so you can interpret it in multiple ways. And in particular, when you integrate 1, this recovers area. There's an important analogy here to integrating the function 1 in the single variable case. If I integrate 1 over an interval, this is an easy single variable integral to do. The antiderivative is x, plug in b, plug in a, and subtract, and we get b minus a. And on the one hand, this is the area under the curve 1 from a to b. But because this has height 1, this actually coincides with the length of the interval AB. So just like with this double integral, which on the one hand computes volume but can be interpreted as area, a single variable integral, which we know computes area, in this specific case we can interpret it as length. So moral of the story, in multivariable calculus, integrals can have multiple interpretations.